Hey everyone, my name is Stephen Bogach and welcome to Growing Serverless. Today we're going to be talking a little bit about using Go in order to deploy serverless cloud functions. And the reason I'm specifically honing in on functions is because a lot of the other serverless compute out there is container based, right? So whether you're using EKS or GKE or any other acronym that has to do with Kubernetes or containers, then this talk wouldn't really be applicable to that. So we're specifically focusing on serverless cloud functions. And to talk about this, what I really wanted to do is I sort of wanted to build our story around trying to build our own API. Like let's say we have something that's Snapchat-esque, where we basically want to be able to just create files, retrieve files, and delete files, but all those files will always have some kind of temporal nature. Like they're only going to hang around for so often. And we want that value to just be, at least to start with, a default. So you might ask, well, if we're starting from scratch, well, why would you want to use serverless? And I would personally focus on, one, you only have to pay for what you use. You don't have to worry about managing your own infrastructure. You don't have to worry about, having enough servers in order to handle peak loads at certain times. You don't have to worry about planning, growth planning in terms of as we're acquiring users, it looks like in 2 months' time we might need to double our resources. And it's also fairly seamless scaling. You don't have to worry about preemptively scaling up some or horizontally scaling some amount of servers or load balancers or anything like that. So we know we want to use serverless technologies, and we also want to do this all in Go, which is why we're at the conference in the first place. And we want to make sure that our code is easy to test, easy to iterate on. It's approachable to new developers joining our team as we're growing our team. We want code basically that we can be proud of. So now we get to, we basically want to choose, the stack, because ultimately there's quite a few, cloud function providers out there. We obviously have AWS's Lambda, we have, Google's Cloud Functions, there's Azure App Functions, or function apps. Netlify has a sort of abstraction layer over Lambdas. There's a lot to choose from. Of the ones I've mentioned, though, both, AWS Lambda and GCP's Cloud Functions have the easiest or most straightforward native Go support. And each of these platforms also have their own, blob storage that we can easily use, S3 and Google's Cloud Storage, respectively. Both of them have lifecycle rules, which we can basically use for our time to live setup, and it should be basically fairly straightforward, regardless of which route we take. That being said, most of the talk we're going to focus on AWS Lambda, and the reason being is frankly that AWS Lambda has the lion's share of the market, or rather AWS does when it comes to cloud providers. And I want to make sure that this talk is as helpful to as many of you as possible. All that being said, we will talk a little bit about GCP later on in the talk. So let's get started. And if you would like to follow along the code with code samples as we move through the talk, you can find it by going to that GitHub link. It should be fairly clear where in the talk we are as we work through the slides. So to start off, let's just say we've started our project. We've opened up the repo. And let me move myself out of the way here. So then let's, we've gone to the docs page, and we've started reading, and we find out that apparently we can't just use straightforward, Golang HTTP functions to write our Lambda code. But that's okay. The docs are pretty clear. We just need to make sure we have a JSON encodable object. And as it turns out, there's already some AWS Lambda libraries that can help us out to provide us these objects. In this case, we basically need to use like the API Gateway Proxy Request and API Gateway Proxy Response object, since that's the way that we're going to be able to trigger our Lambda from the public internet. Let me move myself again. So anyways, like we write our code with this object in mind, and it feels a little bit strange to us, and we want to follow best practices. So we can't use our normal kind of like muxers and routers, whether your router or muxer of choice is Gorilla Mux or Julian Schmidt's HTTP router and so on. In this case, we're just using a simple switch statement to basically trigger like the different types of methods that we support on our API. But like I said before, like these objects already feel a little bit unusual, so we're kind of decoupling our code from those objects here. And you can see here in the subfunctions, we basically have no notion of the fact that this is coming from Lambda or API Gateway or anything like that. And this is fine. The decoupling makes this part of the code like a little bit nicer to read, and it also sets us up to be able to test this code independently. The one downside though is as we write these unit tests, we have to basically fake all the input, and it's also input that we're in the real world never really in control of. We make an HTTP call, but then ultimately it's going to be API Gateway that's doing the translation between my HTTP call and the object that I'm receiving. So these tests help, but they don't give us the same kind of confidence that we would get from a real end-to-end test. So what can we do? The easy answer is to let's deploy our code and let's at least do manual testing. Let's see how it works. It's not directly related to this talk, but all the infrastructure for the API that we're talking about here is defined in the repo I previously mentioned as Pulumi code, and so that gives us repeatable infrastructure and declarative infrastructure. And anyways, the deploy that makes the deploy fairly fast. We get to go from from 0 to API in slightly over a minute, and we basically get to update the API on average in less than 30 seconds, which on the face of it is really not that bad. But basically, the more and more you're deploying, the more you're working through bugs. You find that this time starts to add up, and all of a sudden the development cycle starts to get a little bit lengthy and frankly somewhat frustrating. So what can we do basically to do something a bit better, a bit more enjoyable from a developer experience perspective? Well, one option that's out there is to rely on local stack, and local stack basically allows us to use locally running fakes of different AWS services. They support a ton of different ones. There's API Gateway, Dynamo, Kinesis, S3, and quite a few more. And actually, if we were to override all of the AWS default endpoints, we actually get to still use our same Pulumi declarative infrastructure in order to deploy all of this. However, there are downsides. At various points simply as APIs evolve, add features, or fix bugs, the APIs aren't guaranteed to be 100% compatible, and there has been issues in the past where the local stack API effectively wasn't compatible with Terraform, which is used under the hood for Pulumi, and then basically there's certain times when you may or may not be able to deploy your fake local environment. Also, it's a partial abstraction. You don't have the same identity and access management going on, so you don't you know, you will maybe encounter some of the bugs you would encounter in production, but you won't encounter all of them. And it might also give you almost a false sense of security in a different direction. So kind of with that, begs the question of, is there a way that we can maybe, instead of trying to solve, this deployment problem, this developer experience problem with tooling, can we solve it with code to some extent? Can we use language patterns, in our favor? And I would say yes. I think to start with, we want to make the code as idiomatic as possible. Before in our POC, we basically just started off, with a bunch of, with a bunch of files all in package main. We were just trying to get something up and running. And now it's like, okay, we're taking a step back. We want to make things a little bit better. And also, we think about how would we write an API in Go if we weren't using Lambda? And the obvious answer is, we'd be using the Go standard library, which is, Go's like HTTP library is phenomenal. And, there's really well-established patterns for writing routers, for testing HTTP servers, that we can basically like rely on. And then we can, on top of that, we can also, sort of abstract away the store. And that can help us out, basically not have to rely on an S3 specific deployment. So this is like the original code layout that I was talking about. As you can see, everything's, just at the package root. And in this new kind of more idiomatic approach, there's obviously more files, but they're also more organized. Like we can, like everything under CMD is idiomatic kind of Go project layout. Each like directory under CMD is a separate binary. Everything under internal is shared code that can be called by other members of the repo. And so these are the new objects that we're dealing with now. And as you can see, the store is, like we said before, it's now abstracted out. We just know that we want these sort of cruddy methods. And basically, like that abstraction now lets us have these two separate implementations, like a local one, which is we're just backing with a map using a lock for thread safety, and then we have a separate S3 implementation that's that's actually S3 native and knows how to deal, how to write files to S3, read from S3, and so on. And now, like our server, which again is in shared code, it's actually like routing. It's basically routing HTTP calls as you'd expect. It's starting up a server like you'd expect. And at this point, you might ask yourself, well, hold on. I mean, what's actually doing the heavy lifting to to talk to Lambda? Like where does that come in? And I'll say, just hold on, because we're getting to that. The nice thing about this setup is that now we kind of can go back to the normal world of Go testing and Go patterns. So for example, here in our test main, we can like set up a version of our server using our local store and starting it and not shutting it down until we're done with our tests. And then our unit tests actually look they're nice. They're a lot more functional. We can we're actually making HTTP calls. We can actually like rely on some like the different aspects. Or the different things that we get from the router. For example, if we were to have authentication middleware and so on, we can actually like test that and leverage that right now. And again, going back to your hypothetical previous question, so what? Yes, like this is how you write an API in Go, but how do you write an API in Go in Lambda? And kind of the answer is that actually there's several tools out there that let us basically translate between a Lambda request and a normal HTTP request. We could write our own, but at this point there's Radio Public Library from AWS Labs, and there's a few other libraries out there if you were to search for them. And what this lets us do then is, like, since all of our shared code is effectively standard Go HTTP server, abstracted away the store. What this lets us do is only worry about the fact that one of our entry points is HTTP and another one is a Lambda API gateway proxy request. Lets us defer that decision just to our mains. And now this is where like that project structure comes into play, and we can actually build two different binaries depending on what we're trying to do. So for example, here like like we build a local binary, like we're hosting it port 8080, and we can easily just like just call it with some random payload. We get it to under OK. Like it gives us our UUID back. We use the UUID to retrieve the object. It's what we expect. And basically, in this cycle, just starting it up locally and getting to try out different calls, maybe different edge cases, things that maybe don't make sense to necessarily have in unit tests, or just edge cases that you just want to run through out of curiosity, or you just haven't written the test for yet. And basically, the way that we build these two different binaries is just relying on a fairly simple makefile. And the way we don't, as you can see, the difference is effectively when we're building the Lambda, we need to make sure that we're specifying like the Linux operating system target. If your machine also wasn't MD64, your makefile, you probably would also want to specify that the Go architecture should also be AMD64. As you can see, like the only difference is really kind of like that target folder that's getting built. So that was that's a fairly nice clean abstraction. We can easily create the local binary. We can create the Lambda zip. We know that the code is mostly shared, so we feel good when we're testing things locally and then ready to deploy them to the crowd. But is there what else could we do in order to like increase our deployment flexibility? Because like we said before, realistically, like we just arbitrarily chose to use AWS Lambda as our compute platform, but there's no reason why we couldn't use Google Cloud Functions instead. And kind of the answer to that is the Google Cloud Development Kit. And basically, the development kit is like built and maintained by a specific team at Google, and it's a set of libraries that kind of like abstract away some of the commonalities between the different cloud providers' offerings. And there's drivers for different SQL tools. There's drivers for different blob storage tools, and several more that you can find in there. And in this specific case, actually, the kind of like the abstraction provided by the blob package has everything we need. All we really need, right, is we need to be able to write the files, to read the files, and delete the files. So what that lets us do now, for example, in our unit tests, in this like server setup that we briefly looked at earlier, all we have to do is just open up like this this file blob, and as we're now requiring a file blob instead of our own store interface, that works great. And we can also it gives us some flexibility where we can have our if we want to exercise a little bit more of the full system, as opposed to using a local backend when we're running locally and using a remote backend when we're deployed remotely. We can actually also test out that fact that our the actual blob package is doing what we expect it to, that we have our credentials correctly set up, by basically choosing either the local store or at the S3 store when we're actually going to start up our local main. Now, I mentioned that we'd be getting into Google Cloud Functions in a bit, and there is one particular nuance to using it, and that's that unlike when you're running this locally, or when you're using an AWS Lambda, there's actually a different entry point. For both Lambda and just a normal HTTP server, your entry point to the code would be package main, and you would be effectively like setting up a TCP listener, and then on that TCP listener, like you're hosting your server, which is where you usually see all that listen and serve, kind of boilerplate in package main. But for the Google Cloud Functions, actually, the way that they're actually hosting it is they're basically running their own main, then calling out to some package that you define and some handler that you define. So because of that, our entry point code has to look a little bit different. It's no longer in package main. As you can see, we're doing more in init. We're not, we're parsing the config flags out of init rather than doing them in main, because again, that would overlap with the main that's already being run by Google Cloud Platform. But we can elide that without too much trouble, like basically by using a little bit of like makefile trickery. And if you're following along with the code, or if you want to look this up after the talk, basically all that makefile is doing is sort of copying, it's creating a temporary directory and copying the files in the format that's expected by Google Cloud, and then just zipping it up. And then we're, again, using Pulumi to do the actual deployment. And here we can see actually that, we're basically actually calling our Google Cloud Function. The Pulumi stack output bit that you can see there is just asking Pulumi to give us the URL that got created on that deployment run. And you can see again that it's running on Google. You can see that the server header is telling us that this is coming from the Google front end. Again, you can see that we were able to create the blob. We were able to read the blob, and we did all this with no extra code. In fact, we did it with less code. We basically got, if you look at this like directory structure now, before where we had a few extra files. We had our store.go, s3store.go, local store.go, and obviously like the associated tests for them as well. So now we actually with less code, we actually got the ability, again with the additional makefile trickery, but basically to deploy to a third environment. Now we can deploy locally, we can deploy to AWS, and we can deploy to GCP. And now the question is, once again, can we do more? Is there a different way to do this? And at this point, I would say that this is almost more a question of taste than it is of functionality necessarily. Because we're already at a place where the repo structure feels pretty natural, it's pretty idiomatic. We can just use different make build targets depending on what we're trying to deploy, or if we want to run something locally. So overall, we have a lot of what we set out to have at the onset of the talk. That being said, though, there's another fairly idiomatic way that we can achieve this same thing, and basically we can do this by looking at what a lot of Go cross compilation already does, and that's basically to use build constraints, which are also known as build tags. So what are build tags? Well, if you're not already familiar, build tags are effectively a comment that goes right above your package definition, where you're basically annotating the file to let the compiler know whether you want to include that file or not for certain compilation targets. So for example, if you were to use a build Linux tag, that would mean this file is intended to be used for Linux builds or for Darwin builds, and so on. And you can see here an example of how this changes our makefile a little bit. Now, instead of basically changing the path that we're looking at in order to build the different binaries, what we're doing now is we're passing that tags flag through to to the compiler and specifying that we want to build, the AWS version of this binary. And this is kind of, we're kind of skipping a little bit of the code here, but you can basically see like what like the serve, this can be found in like a CMD toy, serve aws.go, and that's and basically you can see like here, this is what we're telling the compiler what I want to include. For example, like the variable, chi lambda doesn't exist outside of the scope of an AWS build. The function handler doesn't exist outside of the scope of an AWS build. GetStore actually does if you were to look at the non-AWS build tag, and you could see that it's specified there as well. Only there it's running on the file blob, or using the file blob rather than the S3 blob in order to create our store. So this is again not necessarily better. We do get to basically duplicate a bit less code. They do share the same main, although main is somewhat lighter. And there's other kind of like edge cases as well. For example, going back to what we were just talking about, the Google Cloud Functions, because they have a different entry point, you couldn't just arbitrarily choose using build tags, which files are included, because you would be actually using an entirely different package structure. So this is clean in some scenarios, and it's not as clean in other scenarios. And anyways, we've effectively reached the end of our talk. And just to give a recap, we to start with, we basically wrote code that was very straightforward, very basic. Everything. We kept everything at the root of our project. We abstracted a little bit, but not too much. And this was definitely functional. But a lot of the pain points arose out of having confidence in our testing, in the developer sort of life cycle, and like the amount of friction that adds to the experience. So then we iterated, and when we iterated, we started using the Lambda proxy library, and we also switched to using a more standard Go package structure. And that let us have most of our code be completely agnostic to the fact that we might choose to deploy on AWS, and just limit our knowledge of AWS and API Gateway and Lambda simply to the entry point. Then we iterated a bit more. We brought in the Google Cloud Development Kit, and we basically were able to expand and deploy to a whole new environment. We were able to delete code. And finally, we looked at build tags, and basically, if we were to summarize the difference between like build tags and the separate binary approach we were using earlier, it's effectively deferring the responsibility to the Go toolchain as to which files should be included for different scenarios. And hopefully that I didn't rush that too much, but I know that we're somewhat under the time constraint. Thank you all so much for attending. These are extraordinary times, and I'm just really thankful for everyone who made this conference possible, for all of you for attending. And please feel free to reach out to me. My email is steven@bogach.io. You can also find me on Twitter at bogach.io. And well, again, thank you all, and I hope you have a great rest of the conference.